So we're going to continue on looking at the reduction reactions in terms of those half reactions, and we're going to start with the example that we had on page 2 and do a little more with it. So we had the reaction with with silver nitrate and copper, where we said that the silver ions were going from silver and the copper was going from metal to ions. So if we look at those two half reactions we had talked about on page 2, we can see that the copper has 2 electrons and the silver only has 1. So we want to multiply so that they get the same number of electrons. So this is kind of like finding a common denominator when you're adding fractions. So we need 2, or another way of thinking of it is it's like balancing equations, because that's what it is. So we need twice as much of that reaction, so we end up with 2 silver plus 2 electrons gives us 2 silver, right? Everything here we multiplied by 2. So now our 2 electrons here balance out our 2 electrons here. So if we put the whole thing together, we could say we've got copper plus 2 silver plus 2 electrons gives us copper ions plus 2 silver metal plus 2 electrons. But the 2 electrons are going to cancel out. So this leaves us with copper plus 2 silver ions gives us copper ions plus 2 silver. If you compare that to the balanced equation on page 3, which we had everything showing, now we can see in our net ionic equation, we take out everything that appears on both sides. So the only thing that appears on both sides is our nitrate ions. If we take those out, it looks just the same. So those ones we can leave out because they are the spectator ions, which we leave out of a net ionic equation. If we leave them in, we have what's called the complete ionic equation. So that's some chemistry from the grade 11 level. So we're going to take some more reactions and look at these half reactions, splitting it apart and using that to look at what's happening with those electrons and also to balance the equations. So our first example, we've got zinc chloride and hydrogen. So, hydrogen chloride and zinc. Zinc chloride and hydrogen are products. So if we look what's going on, our zinc is going from zinc metal to zinc inside this compound, which we can figure out, since chlorine's -1, the zinc must be +2. So we have +2 from neutral, so it had to have lost some electrons. This is always a little bit tricky because electrons are being negative, so when you lose electrons you get more positive. So a loss ends up with positive, so we always got to keep reminding ourselves of that. I don't think it becomes intuitive for anybody. If we look on the other two reactants, right, we've got the hydrogen ions and the chloride ions. Well, which one is the other thing that's changing? So if we look, the hydrogen's going from ions to hydrogen gas, the chloride's going from ions to ions. So the chloride's not actually changing, so we're going to focus on the hydrogen. So the hydrogen went from +1 to that hydrogen gas, but first we got to balance our atoms. So hydrogen gas, there's 2 of them, so we need 2 hydrogens here. Then we can look at our charges. So if we have +1 times the 2, we have a total of +2. So to make that balance out with our other side that's neutral, we need 2 electrons. So those 2 negatives are going to cancel the 2 positives. We can also see the 2 electrons in our oxidation are going to cancel the 2 electrons in our reduction. So our net equation, we can just add zinc plus 2 hydrogen, and we get our zinc ions plus our hydrogen gas. The electrons cancel out. Do remember to show your states for those overall reactions. I'm not too picky on the intermediate steps, but for your final reaction, you really want to be nice and clear. So moving up the difficulty a notch, this next question is kind of similar. We're given this unbalanced partial reaction, but what's different about it is that it's in acidic solution. So that in acidic solution tells us, oh, we might need to add some other stuff in order to make this balanced. So what does balance and what doesn't balance? What works here? Well, if we look we can see there's one substance that's a little easier to figure out which way it's going, and that's our tin. It starts out at +2, ends up at +4. So that's a difference of 2 electrons, and did it lose or gain them? Well, it got more positive. So remember, more positive is a loss of electrons, and loss of electrons, that's our Leo. The O is oxidation. So we know that one's oxidation. That's the easier chunk. The tougher chunk, well, we can figure out if one is oxidation, the other thing must be reduction. So the dichromate somehow ending up with chromium 3 ions has to be reduction. So we'll have to figure that one out in a little more detail, but we know which direction each is going. So we'll write down the easy one first, oxidation in this case, going from +2 to +4 and loses 2 electrons. The reduction is going to be a little more complicated because we have these extra substances involved. And specifically, if you look, your dichromate has oxide ions, and there's nothing, sorry, oxygen, not ions. There's nothing that's oxygen on the other side. So we balance the things we can first. So if we have chromium and there's 2 of them here and only 1 of them here, we start by saying, okay, let's balance the chromium. Then we have to look at, okay, how do we balance those oxygens? Well, if it's in acidic solution, there's 2 substances we can add. So the acidic part tells us we can add hydrogen ions. That doesn't help us balance the oxygen. The solution part tells us we can add water. That does have oxygen in it, so we can add water where we need some oxygen. And how much oxygen we need? We need 7 oxygens, so we're going to add 7 waters. Let's make that the same color as everything else. Now that made things not quite match up because our hydrogen on this side doesn't balance with any hydrogen on this side. So now we have to add some hydrogen. And since it's in acidic solution, that hydrogen is going to be in the form of hydrogen ions. We could also say hydronium ions, but that adds a level of difficulty we really don't need to bother with in this section. We know from our acid-base section that it does make sense to put it the other way as well. So now we've got 2 chromiums, 7 oxygens, 7 oxygens, 14 hydrogen, 14 hydrogen, but our charges don't balance out. So if you look at our charges, we have -2 and +14, so a total of +12 on the reactant side. On the product side, we just have 2 times +3, so that's +6. So they differ by 6 electrons. We have to decide where those 6 electrons go. There's 2 ways we can look at this. One is, remember, those electrons are going to cancel some of our positive charge. So if we put it on the side that's more positive, that cancels some of that positivity on that side. So now we only have a +6 on this side to match the +6 on the other side. The other thing we have going in our favor in this question is we have already done the oxidation question, and we know by default this has to be reduction. So if it's on the product side in the oxidation, it has to be on the opposite, so the reactant side in the reduction. We also see here that those don't match, right? We have 6 electrons here and only 2 electrons here, so we need to multiply our oxidation. So what do we multiply 2 by to make it 6? 3. So remember, multiply everything. Multiply the tin 2, multiply the tin 4, multiply the electrons. So now our electrons are going to cancel with our other electrons, so we just need to write our overall equation. So on the product side, on the reactant side, we're going to have dichromate, 14 hydrogen ions, and 3 tin +2. On the product side, we have chromium, chromium +3, 7 waters, and 3 tin +4. It does not matter which order you end up putting them in as long as you show reactants on the reactant side, products on the product side. Now there's 2 more I'd like you to try that aren't in the student handout. So I suggest you pause the video and try these. I will point out, at this point, you probably can do question A quite easily, but question B is a little trickier. So if you get stuck on some part of question B, start the video up again and watch for the solution of that one. I'll give you a hint, right? It's a basic solution. So with the acidic solution, we could add hydrogen ions and water. With the basic solution, think about what you can add. So moving on to the answers, if you've paused or not. Oxidation in our first reaction, we can see the magnesium is going to +2, right, from neutral. So it is losing 2 electrons. The chromium is being reduced from +3 to +2. It's one of our multivalent metals, right? It can have more than one charge. So it's gaining 1 electron to change charge. And we can see again that when we look at that, we've got 2 electrons on the top equation, 1 electron on the bottom equation. So that doesn't balance out. We have to multiply the bottom equation by 2 so that our electrons match up. So 2 electrons here are going to cancel our 2 electrons there. Magnesium plus chromium 3 ions on the reactant side. Magnesium ions plus chromium 2 ions on the product side. So we get this overall. Now, one thing you might have done when you tried question A is you might have said, well, it's balanced because I've got 1 of everything. But what you didn't have 1 of everything of was the charges. If we look at the charges in that original question, we had +3 on the reactant side, and then 2 plus another 2 on the product side. So the charges didn't balance. We've got 3 on one side and 4 on the other side. If you look at the new balanced equation, now that we've taken into account the electrons, we have +6 on the reactant side and 4 plus 2 for a total of 6 on the product side. So the charges didn't balance in the original, but they do now. Now the oxidation for the next one is not too bad. It's tin, goes from metal to +2 ions, so we have those 2 electrons. The reduction is the one that's a little tricky. So if we look at the reduction, by knowing that the first part is oxidation, we can figure out, okay, that manganese must be doing some kind of reduction thing. It starts out as manganese oxide, ends up as manganese. So we've got 2 methods we can use for this. So the first method, we add in base and water to get the hydrogen and oxygen to balance. Because they both have hydrogen and they both have oxygen, it does involve some trial and error, but we have a couple things going in our favor. We know we need to add OH on the side that needs more oxygen, and we're going to need twice as much of it as the water to make the hydrogen balance out. So we basically do trial and error, adding them to each. So we have no oxygen on the reactant side. We do have, said that backwards. We have oxygen on the reactant side and no oxygen on the product side. So we know we need to put the OH on that side and the water on the reactant side. And it's got to always be in a 2-to-1 ratio. So first thing we might try is 2 hydroxide and 1 water. Then we check, does it work? Well, we've got 2 plus 1, 3 oxygen on this side and only 2 oxygen on that side, so that didn't work. Okay, so let's double the water and double the hydroxide. See if that works. So now we have 2 plus 2 oxygen and 4 hydrogen. We have 4 oxygen and 4 hydrogen. Hey, our oxygen, hydrogen balance out. So there is some trial and error, but it's always with that twice as much hydroxide as we have water. And always the hydroxide goes on the side that needs more oxygen than what you started out with, right? So we put it on the reactant side here because we had no oxygen to start with there. Okay, so that balances our hydrogen, our oxygen, and our manganese. Now we need to look at our charges. So this side's neutral, nice and easy. This side we have +2 and -4, so a total of -2 on this side. So to balance that out, we need some negatives on the other side. So the only thing we can add in to balance out our charges is those electrons. So we've got 2 electrons that we're going to add to this side. So now we can see we've got 2 electrons here, 2 electrons here. So we don't actually need to multiply. We can say we multiply by 1 and multiply by 1. So then our overall equation, we take our reactants, oh, I think I put my overall equation at the bottom. After method 2. Right, so we take our reactants, we take our products, we cancel out the electrons. The thing I'm missing in my answer here is those extra waters and hydroxide. on one line. And don't forget states, which I nearly did. So that's method 1. And method 1 works perfectly good. You don't necessarily need to do method 2, but some people like it better. So method 2 is actually the one that the textbook uses, so I'm going to mention it. So in method 2, you balance it as though it's in an acid, and then you neutralize the acid. Now, this is just a gimmick. You're not actually neutralizing an acid. You really would have that same reaction that we figured out here. So with this one, our MnO2, if we're doing this with an acid, we would be adding water to this side. And we would add 2 waters to make the oxygen balance out. Then we would add 4 hydrogens to make our hydrogen balance out. And then lastly, we would have to look at our electrons. So we have +4 on this side, +2 on this side, so we would need 2 electrons. So that's how we would balance if it was in an acid. But it's not in an acid. So what we end up doing is we add base to cancel all of our acids. So in this case, we actually end up adding 4 hydroxides. Whoops, I put an enter in there. And we add 4 hydroxides to the other side. Now what happens when we do that is the 4 hydroxides and 4 hydrogens are actually a water. Right? If you look at that, that's actually water. And over here, we also had a water. So we've got 2 waters to cancel out. So we get left with the same equation that we had up here. Right? We cancel out those 2 waters. We're left with 2 waters on this side and no water on that side, and 4 hydroxides. So it's another way to get to the same place. We still end up saying, oh, we've got 2 electrons in our oxidation, 2 electrons in our reduction, multiply by 1 and add them to get the overall equation. So that's where we're going to stop this lesson. See you later.